Okay. Hello, everybody. My name is Adam Herrmann, and I'm recording a talk that I'm going to give at the 2022 Astrodynamics Specialist Conference here in Charlotte, North Carolina. And the talk is on reinforcement learning for small body science operations. Before I get started, I'd like to thank my advisor, Dr. Hans-Peter Schaub, and I'd also like to thank the NASA Space Technology Graduate Research Opportunity for funding this work. So a quick overview of the presentation. Going to go through the motivation for my work in general, but specifically this problem. Then I'll discuss the small body science proxops problem we've selected, discuss deep Q learning, the algorithm we use to solve it, and then present some preliminary results on both deep Q learning and a reference mission scenario we developed. And then I'll end with conclusions and future work. So the motivation for the problem. My research focuses primarily on planning and scheduling, really using reinforcement learning for planning and scheduling. Traditionally, though, planning and scheduling is a ground-based process. So pre-launch, you have some iterative process between science and mission planning to kind of hammer out a mission concept and a design for the mission. And then post-launch, this can also occur on a periodic basis, so week to week or month to month, where you're kind of defining some of these finer points. When are we doing exactly what science? When do we perform our trajectory correction maneuvers, et cetera, et cetera? This is all passed to some activity planner, which then generates an activity plan, which is sequenced and uplinked to the spacecraft for execution. This process has worked really well, but for the past few decades, onboard planning and scheduling has been posed to address some of the problems introduced by ground-based planning and scheduling. And namely, those problems include the time delay, so the solve time and the round-trip light time delay. You also don't have a perfect model of the environment and the spacecraft, so you can have mismodeled task execution times or mismodeled resource consumption that necessitates replanning. And you can also miss opportunistic science events if they occur at a frequency that is higher than your time delay, right? So onboard planning and scheduling has been used quite successfully. On the right-hand side, I have some diagrams from the Earth Observing 1 mission and also the IPEX CubeSat. But really, onboard planning algorithms are reserved for replanning activities. So you have some a priori plan developed on the ground that's then used for replanning in case something goes wrong. More work is required for kind of fully autonomous solutions that don't really require some a priori ground-based plan. So that's where reinforcement learning kind of, I think, comes in. So basically, RL is learning how to map situations to actions to maximize a numerical reward signal. And it's really well suited for onboard planning and scheduling due to the potential for optimal policies and that it's closed loop planning. So you can kind of think of it as replanning at every time step, selecting the next optimal action based on the observation you receive from the environment. And if you formulate a POM-DP, you can include state uncertainty in your problem formulation and also your solutions. So what exactly are we posing here with RL-based planning and scheduling? I'll start with what we're not proposing. What we're not proposing is going to the environment with your spacecraft in real life, basically, and just learning what to do. I've seen some work that suggests for some problems that might be possible, but for planning and scheduling type problems, I really don't think that RL would be well suited for that, namely because of the amount of environment interactions it takes to learn something, and doing that safely is extremely difficult. Instead, what we're proposing is replacing that activity planning block with a training block. And instead of uplinking to the spacecraft a sequence of activities, you uplink this policy, which is then executed closed loop onboard the spacecraft to come up with your the next action based on your observation. So big picture for small body proximity operations, where would we eventually like to take this work? Well, I'll start with past work, what's been done in the literature. There's a more detailed summary in the paper, but here I'm just going to provide some highlights of kind of some of the issues in terms of planning and scheduling, right? So really the literature mostly focuses on RL for controls and guidance problems, typically for some objective function that includes surface imaging or mapping for shape modeling. There's little or no treatment of resource constraints. You might have some treatment of it, but Power is one example that's almost always left out. And while a lot of people formulate POM-DPs, really they're just adding noise to the state. It's really unclear how the state uncertainty affects the learned policy, and what kind of algorithm should be used to best handle that. So there's elements of planning and scheduling problems, but it's not really a comprehensive treatment of planning and scheduling because they're just not those types of problems, which is fine, but we'd like to explore those. So what are some of the research goals longer term? Well, kind of investigate the small body proximity operations problem. How do you formulate it? How do you formulate it starting as an MDP? How do you include the state uncertainty and solve the problem? And then what's the effect of this state uncertainty on the science return and the quality, the system safety? How does it impact your learned policy? These are the kinds of things that we'd like to look at. So now I'm going to talk about the small body proximity operations problem that we've selected. So I looked at a bunch of different mission phases from Rosetta and OSIRIS-REx and kind of tried to categorize them. We landed on wanting to look at science operations in particular. And this problem took a lot of inspiration, if you will, from the detailed survey phase from OSIRIS-REx. I'll talk about some of the similarities and the differences here in a moment. So our problem formulation is to maximize the weighted sum of surface targets imaged and downlinked, and the amount of spectroscopy map collected and downlinked while avoiding resource constraints and collision with the body. The resources that we're concerned with are power, onboard data storage, and fuel. We use the deep space network for downlink. There are physical and temporal constraints on the DSN. So physical being basically just range and elevation, but temporal being, the spacecraft can only communicate with the DSN within some time slot once every 24 hours. So it's about 2 hours every 22 hours, let's say. To complete these objectives, the spacecraft maneuvers between a set of waypoints that we define in the Sun asteroid hill frame, and we model the problem using the Basilisk Astrodynamics software. So the waypoints are all defined in the Sun asteroid hill frame. We have 6 separate solar longitudes and 6 separate solar latitudes. That's 36 waypoints in total. Mapping occurs at 3 of the solar longitudes, so -30, 30, and 90 degrees. You can see those pictured here with the dashed lines. And the spacecraft, so kind of different from the detailed survey phase, instead of just maneuvering from north to south or south to north, we have some intermediate waypoints, some intermediate solar latitudes. The spacecraft can do science at any of these, instead of just constraining it to like a very narrow band that lasts only a few hours. So some more detail on the mapping and imaging targets themselves. Like I mentioned, there are 3 maps that need to be collected. These are collected at specific solar phase angles. Each map is really just a collection of points evenly distributed on the surface of the body. And we have several mapping requirements as well. So the spacecraft must be within 1 degree of the solar longitude of the desired map. The spacecraft also has a 22.5 half angle field of view of the instrument. And the spacecraft must be within 45 degrees of each mapping point to successfully collect it. So all of those conditions must be true for mapping. For imaging, it's pretty simple. We have 10 imaging targets distributed on the surface of the body in some set T. There's a 60-degree elevation requirement that the spacecraft must be within, and then there's also like an attitude requirement because it points an instrument at the target itself. So now I'm going to talk about the Markov decision process formulation. Specifically, I'll begin with the state space. So we include some geometric information, position and velocity of the spacecraft, position of the nearest ground target, position of the current and previous waypoints, and all of these are expressed in the Sun asteroid hill frame. We also have several resources. So what's the percent fill of the battery? What's the percent fill of the data buffer? And then how much of our delta V budget have we used? We also include an eclipse indicator and then a state that basically counts down from 0 to 1 until you have DSN access. 1 just means you have DSN access. Anything between 0 and 1 is like, this is the percent that you have to go until you achieve that. And then we have some states on the science itself. So we break the body of the asteroid into several different regions, and we say what percentage of each of those regions has been mapped. And then we also have states on the number of image and downlight targets. It's important to mention that, this is an MVP. We have observability on these things. When we move to a POMDP formulation, there are things in the state space, like the map regions and the number of image targets that might have some uncertainty on them, or we can't even observe them at all. So, but that's kind of for future work. But just to kind of get your thinking in the right space. So for the action space, we have a few different modes. We have a spacecraft charging mode. We also include 8 waypoint transitions. So we have 36 waypoints in total. The spacecraft can only maneuver to neighboring waypoints. And then we have mapping modes, imaging modes, and a downlink mode. A quick note on the waypoint transitions themselves. I mentioned only neighboring. So here I kind of have two different transitions. So the dotted green lines, those are kind of nominal transitions, right? That's when you don't have to do any sort of angle wrapping. But the solid red lines, that's when angle wrapping is required. Typically, there's no danger of collision with the body, except for when you're going from the southern to northern latitudes or vice versa, north to south, you will collide with the body. So the agent has to basically learn, don't do those transitions. So we formulate a piecewise reward function. I won't go into detail of the specific notation, but I'll just kind of talk you through it here. So the first condition we check for is failure. We return -10 if the spacecraft drains the batteries, overfills the data buffer, exceeds the delta V budget. And then if no failure occurred and we entered an image mode, we loop through all of the imaging points and we return some small reward bonus for every target that was imaged successfully for the first time. We do something similar for the mapping mode. So we just loop through all the mapping points. Were they mapped, yes or no? Okay, here's a small reward bonus. And then if we enter through the downlink mode, we loop through all of the imaging targets and the maps, and we return a large reward bonus for any that were successfully downlinked. If none of these conditions are true, we just return 0 reward. Now I'll talk about deep Q learning. So here's the algorithm we use to solve the problem. So basically deep Q learning just solves for the optimal state action value function, which is the expected value of all future return given some state in action following the optimal value, the optimal policy pi. To do this, deep Q learning explores the environment and then uses some loss function to correct the weights and biases in a neural network. The loss function is given there. Basically, we just sample from some replay buffer, compute the loss. I think our batch size is like 10,000, so pretty large. And then every n steps, we deploy the policy for evaluation in the environment. I'll discuss them preliminary results. So here's the reference mission scenario. This plot on the right-hand side is in the Sun asteroid hill frame. So we designed a reference mission scenario to just validate the simulator, make sure that we had parameterized it correctly, and also to develop an upper bound on the reward. So I'll kind of talk you through the activity plan, so to speak, this reference mission scenario. So the first thing that happens is mapping from southern to northern solar latitudes. Then we enter a charging mode and transition to a new solar longitude. Then we start the mapping process all over again for the second map we now want to collect. And then we stop, we do a couple of charging modes, we downlink to the DSN, and then we start mapping again from north to south, do another charging and transition maneuver here, and then we start our mapping over again. Once more, about halfway through, we have to charge and downlink. Then we charge, transition, continue the mapping, then we charge and transition to the last solar longitude, where, we do maneuvering from north to south, and we image the entire way down in between maneuvers. So here are a few plots on the map progress itself. So we have each of the 3 maps we want to collect, 90, 30, and -30 degrees. And you can see that qualitatively, we're collecting most of the maps. I think each of these is above like 95% collected, which is great. That's kind of what we wanted to see with our reference mission scenario. And then here are a couple plots on the stored data. So that's the plot on the left, and then the DSN access on the right. So you can see we're taking advantage of every downlink interval. If the agent did not, and he's continued mapping, it would overfill the data buffer and fail. So it's important that it hits each one of these access times. And then here's something, a diagram on the reward. So basically everything before step 80 is all mapping, right? So mapping, collection, and also downlink. And then that large jump there at the end, that's from imaging. So you can see those two components are about equal. So we kind of threw deep Q learning at this problem, took a few iterations. We ended up getting this reward curve. But you can see that we only get between 10 and 15% of the maximum reward. And this is with equal components for mapping and imaging. And this really is not what we want to be seeing, right? We want to see something more like 90%. So this is pretty normal. It takes a while, I think, to kind of get the right algorithm, the right parameterization of that algorithm, but also the correct parameterization of your environment and your Markov decision process. So the next thing I did was kind of increase the reward component for mapping such that it's roughly 3 times that of imaging. And the reason for that is because it takes, one mapping campaign, right, to collect one map. It takes just about as much time as collecting all of those images, right? So here you can see that when we normalize the reward again, we get between 20 and 25% of the maximum reward. This isn't the 90% we want to see, but it's a lot better. So it's kind of steps like these that we have to take and kind of iterate on the problem until we get the performance that we want. So I'll discuss conclusions and future work. So we formulated a small body science operations problem as a POM-DP, and we generated preliminary results with both a reference mission scenario and deep Q learning. We found that deep Q learning hasn't quite yet performed like we want it to, but for future work, we're going to finish parameterizing the MDP, and we're going to finish parameterizing the algorithm that we're going to use to train a good policy. And then I'd also like to add a more representative GNC subsystem on board. So attitude control, we do that pretty well, but I'd like to add some kind of optimal two-burn solution for those waypoint transitions. And then also, as we move towards a POM-DP formulation, have some representative navigation system on board that's either a hybrid with ground-based observations and onboard observations, or just fully onboard autonomous nav. And then finally, once we formulate that POM-DP, solve the problem, a lot of work there in that third bullet. We'd like to investigate the effects of state uncertainty on science return and system safety. Here's a quick slide on the references, and that's the talk. So thank you all for tuning in, and I hope you enjoyed it.